So what we're starting now is very similar to what we just did on the review problems, but it's given graphs. So if we take a look at this first graph, I know if you printed it, if it's black and white, it's probably hard to tell, but the blue one is f of x and the red one is g of x. So on the first one, I have f plus g of 0. So that is f of 0 plus g of 0. So if I'm looking at f of 0, that would be 5. Oops. And then g of 0 is 0. So we get 5 plus 0, so that's 5. And so f plus g of 3 would be very similar. We are just doing f of 3 plus g of 3. So I'm following the blue curve. So f of 3 is 4. And then g of 3 is 3. So we get 7. Any questions on those? So if I had, it says when is f minus g of x equal to 0? That would be when they intersect. So if you're looking for basically when f of x minus g of x equals 0, that would mean if I add g of x to both sides, when f of x equals g of x, that means f of x minus g of x would be 0. So at that, we have this point here and this point here, they're intersections. That's where they're equal. So for that first question, I'm just going to label this A and B so I can write it down below. It would be when x equals, and we're just going to approximate this, negative 3.5-ish, and at x equals 3.5-ish. So at those x values, those two functions are intersecting, so they are equal. So if you were to subtract those values, it would equal 0. And then similarly here, it says when f minus g of x is greater than 0, so when f of x minus g of x is greater than 0, that would mean that where f of x is greater than g of x, if I add g of x to both sides. So that's going to be right here, right? From this x value to this x value, all of those values in between, f of x is above g of x, right? So I'm going to give a whole inequality of answers here. So for part B, when x is greater than negative 3.5 and less than 3.5, that's when f of x is going to be greater than g of x. So f minus g of x would be greater than 0. Any questions? And notice how I'm using just greater than and less than, not equal to, because this is asking specifically greater than 0. So if I wanted greater than or equal to 0, I would have or equal to on both of those. Any questions on that? Okay, the next one is pretty similar. So we're finding finding f of 1 minus g of 1. F of x is, I really should have just stayed consistent with this, but f of x is now the red one, and g of x is now the blue one. So f of 1 is 3. And g of 1 is 1. So 3 minus 1, we get 2. And then f plus g of 4, that would be f of 4. So that's 2 plus g of 4, which is 3. So we get 5. Any questions yet? Okay, the next pieces here, let's see, I'll label them A, B, and C again just in case I run out of space. So we're looking for when f minus g of x is greater than 0. So again, that's when f of x is greater than g of x. So that's going to be from here to here. So -1 to 0. So -1, I'm going to include -1 on this one because it's still greater than g of x, f of x is still greater than g of x at -1. And then less than 0. And then from 0 to 3. On part B, it says when is f minus g of x less than 0. So that would be when f of x is less than g of x. So when the red graph is below the blue graph. So that would just be right here. So we have from 3 to 4 and including 4. Because it's still, the red graph is still below the blue graph at 4. And then where are they equal? We're looking for the intersections. So we'll just say when x equals 0 and x equals 3. So that is all the same like stuff that we did, but just with graphs given instead of with the functions given. I could also ask a question, something like find f of g of, let's do -1. So that means I'm going to find g of -1 first, because we sort of work with the inside first and work our way out. So g of -1 is 1, right? So if I plug in 1 for g of -1, that means I need to find f of 1, which is 3. So that's how I would do compositions. So you can still do compositions. I know I did all operations here, but you can still do compositions with functions given graphs. All right. So if there are no questions on that, I have types of symmetry. And this will finish up our last little bit that will be appearing on your test on Wednesday the 2nd. So I sort of broke down every type of symmetry into sort of bullets, and this is exactly what line or which each type of symmetry looks like and how we would test for it. So the first type of symmetry is line symmetry. So we have a couple different types of line symmetry that we're going to be looking at. And so the first one I have here is symmetry in the y-axis. So if we have symmetry in the y-axis, it means that whenever xy is on the graph, so is negative xy. And off to the side here, this is what line symmetry would look like. So we've done this already when you had an axis of symmetry on your parabolas. It just means that that line of symmetry would be the perpendicular bisector connecting any 2 points on your graph. So what we would do to test for this is take negative x, plug it in for x into our function and simplify. And if we simplify and we get back the same exact equation that we started with, then it would have symmetry in the y-axis. So that would be something like if we had a function y equals x squared. If I plug in a negative x into that and I simplify it, it gives me back y equals x squared. So since I get simplified to get the same exact thing, it would have symmetry in the y-axis. The next one here is symmetry in the x-axis. So it's very similar. It just means that x negative y is on the graph whenever xy is. So that means I could plug in negative y in for y in my function and simplify. And if I get back the same exact function, then that means there's symmetry in the x-axis. And then symmetry in the line y equals x means yx is on the graph whenever xy is. So what that really means is if I have a point like 3, 7 on the graph, and I have symmetry in the y-axis, that means 7, 3 is also on the graph. So to test for symmetry on that, what we're going to do is swap the x and y positions in our function. So I plug in y in for x and x in for y and simplify. And if it comes back to simplify this as the same exact function as we had in the beginning, then it has symmetry in y equals x. So that is all line symmetry. And then the next piece here, we have some point symmetry. So point symmetry means that there's a point that's the midpoint of any two symmetric points on your curve. So we've had that when we did cubics. We said we had a point of symmetry rather than like an axis of symmetry like we do on a parabola. So the type that we're going to be testing for is symmetry in the origin. So if the origin is the midpoint, then you'll just have opposite signs on your x and y values. So if you have xy on your graph, then negative xy would also, or negative x, negative y would also be on your graph. Because if you found the midpoint of that, it would be 0, 0, right? So what we're going to do to test for it is switch the signs on x and y and simplify. And if it comes back to be exactly what we started with, then it has symmetry in the origin. So we're just going to go through a bunch of these examples here and check to see what types of symmetry we have, if we have any. All right, so I like to write myself a little bit of a reminder above each of these, so when I'm testing for symmetry in the x-axis, I'm going to be plugging in x negative y. When I test for symmetry in the y-axis, I'm going to plug in negative x, y. When we test in y equals x, I plug in y, x. And when I test in the origin, I'll plug in negative x, negative y. So I'm going to start here, testing in the x-axis. That means I have to plug in negative y in for y. Oops, equals, not plus, equals x plus 1. And negative y to the fourth would simplify to be positive y to the fourth. So I plugged in negative y, I simplified, it gave me back my original. So that means, yes, I have symmetry in the x-axis. So I'll just wait and I'll simplify, and then I'll circle the types of symmetry that ends up working. Next, I'll test out y-axis. So I plug in negative x in for x. And there's really no simplifying left to do. That's all I have. And it's not equal to my original. So we do not have symmetry in the y-axis. And then I'll do y equals x. So I have x plugged in for y. Oops, it's to the fourth. And then I'll plug in y in the x position. I mean, there's not much simplifying left to do here. At best, I could, take the fourth root of both sides if I wanted to, but it's not going to equal what I started with, so this one does not work. And then for the origin, I'm plugging in a negative y in for y and a negative x in for x. So I get y to the fourth equals negative x plus 1. So not equal to what I started with, so no symmetry in the origin. So only symmetry in the x-axis on this one. Any questions there? Okay, let's try another one. So I'll start with the x-axis again. I'm going to plug in negative y in for y. And when I square that negative y, it becomes positive y squared. So that's back to what I started with. So the x-axis, or we do have symmetry in the x-axis for this one. And now I'll test out y-axis. So I'll plug in negative x in for x and simplify. And I get back what I started with. So we do have symmetry in the y-axis. Next, we test out y equals x. So I will plug in y in for x and x in for y. And because I can do addition in whatever order that I want, I can rearrange these, and it's exactly what I started with. So we have symmetry in the line y equals x. And the last one, we have the origin. So I'll plug in negative x in for x and negative y in for y. And when I square them, they both become positive, and that gives me back what I started with. So we have symmetry in all four of these: x-axis, y-axis, y equals x, and the origin. Does anyone know what shape of this graph is? Victoria? It's a circle. Yep. Good. So why don't you give number 3 and 4 a try? Okay, I can see some of you are done, so let's go over these and we'll talk about which ones work. So for the x-axis, we get x cubed minus y cubed equals 1, which is obviously different from this one, so no symmetry in the x-axis. In the y-axis, we get negative x cubed plus y cubed equals 1, also not the same. For y equals x, we get y cubed plus x cubed equals 1, which is the same as my original. So we do have symmetry in y equals x. And then for the origin, we get negative x cubed minus y cubed equals 1, so not the same. So on 3, only symmetry in the line y equals x. Obviously, I don't even know what this graph looks like. X cubed plus y cubed equals 1. So we don't need to know what it looks like in order for us to tell what it has symmetry in. And then the last one here, I plug in negative y in here. And when you take the absolute value of negative y, it's the same as the absolute value of y. And then I don't touch the x's. So the x-axis comes to be the same. So we do have symmetry in the x-axis. In this one, we would have to plug in negative x. So I'm only taking the absolute value of one of them. So this one stays negative. So different from what I started with. So no symmetry in the y-axis. This one here, we have now very different equation. So no symmetry in y equals x. And then the same thing happens in symmetry in the origin. The absolute value of the negative y is the same as the absolute value of y, and the absolute value of negative x is the same as the absolute value of x, but we're still left with this negative x left over. So only symmetry in the x-axis on number 4. Any questions there on the symmetry?